Hello. Hello. pandemic and you are an applied mathematician who has the job of predicting what is going to happen if the things they are continue as they are. And so you see a couple of graphs here. Don't worry if you can't see the text and all, it's fine. So what I want you to focus on is this initial data that these scientists had, and the model that they were using was a very common model called the SIRD model. And what they're looking at is how things will be after a long time if they continued this way. And comparing that to if, at that time, people were still wondering if we would have a lockdown or not. So they compared the effect of having a lockdown to not having a lockdown in through that model, and the eventual behavior is what gave them enabled them to make the predictions there. And but perhaps you are someone who is stimulated by the platonic objects more than the real world data, and for you then the eventual behaviors of some systems like the Lorentz system has a very interesting mathematical structure to it. It is the chaotic attractor, which is the poster boy of chaos pretty much, the Lorentz system. And so yeah, there's multiple reasons to study eventual behaviors of systems or limit sets. In the next 3 slides, I will show you some typical kinds of limit sets that are seen in dynamical systems. And the first one is a very pedantic example of a simple damped pendulum. And on the left, I have drawn the phase space of the pendulum. This phase space is going to be a very common theme in this talk. So if you don't know what a phase space is, it's just a set of all possible states that the system can take. And in this case, I didn't let it run for very long, but I hope you can sort of see that the limit point of this trajectory is going to be the origin, and so that is the fixed point stable set. And the next example I've chosen to add another form of technicality. So this time you notice there is no spiraling behavior or anything. The system starts off at the limit set and it keeps on at the limit set, which means that it is also an invariant set of the system. So what I'm talking about is an invariant limit set. But yeah, just a technical detail. And there's another type of a typical limit set that is seen in systems. Now, fixed orbits, as I've written here, they need not be of infinite number of points as they are here. It could just be 1, 2, 3, 4 points here, and then they could be repeating. And that is also called a fixed orbit. And then the third kind of a limit set that I want to show is the one that I mentioned earlier. It's the chaotic set. So this doesn't have any limit point or any fixed orbit. In fact, if you start a trajectory on it, it'll just keep going on and on and on inside it without ever crossing the point that it started on, or like any other point in the trajectory again. So there is no sense of periodicity here. And even though I've written that this is the limit set of the Lorentz system is actually it's a very complicated object, as I mentioned. It's not this trajectory. I want to emphasize that this is a trajectory on the limit set. Okay. But those are not the only kinds of limit sets that exist. The types that I showed you till now, they are all stable limit sets. So there is a sense of being attracted towards them, and there is other types of limit sets which are unstable. For instance, going back to the first the damped pendulum that I showed earlier, if this is a equilibrium position of the pendulum, then this is also an equilibrium position, just that this is an unstable equilibrium. And so this unstable equilibrium is this point right here in the phase space. And hopefully you can see that if I move slightly away from it, like right here, I will just go along the flow and spiral into the origin again. So if I just push my pendulum like this, it will eventually do something, and then damp out to the bottom. And so there's many reasons to study the unstable limit sets as well. Firstly, the systems, there is a dependence of parameters usually on our system, and if we change the parameter, the unstable limit sets can change their behavior. So from a utilitarian standpoint, from looking at it as it may be something important, as our system can change a behavior to a stable set, we need to study these unstable sets as well. And also, if you attended yesterday's talk, Professor Jim York, he mentioned that if we want to make a graph of a dynamical system, we need to classify all kinds of limit sets that are there in the system, including the unstable ones. And adding on to that point, I think it's just quite natural, from also a standpoint of having a complete knowledge about the system, that if we are studying the stable limit sets, so why not study all different kinds of limit sets? So from that standpoint also, I think it's pretty important to study these sets, and this is also where my contribution lies in the project. I've been collaborating with Professor Jim York, as the first slide said, and my work has been to numerically find these unstable limit sets in different systems, and I'll show you at the end a couple of examples in different kinds of systems that I found out. And the characteristic of these unstable limit sets is, so here I show you a fixed point unstable limit set. And as you can probably see that there is an unstable direction. Unstable meaning that the system is, the flow is going away from the point in these directions, in this and in this direction. And then there is two stable directions as well, that the flow is going towards the fixed point in those directions. And that is a characteristic of every kind of a unstable limit set. There will be a direction in which the flow will move away from the fixed point, and there will be a direction in which the flow will move towards the fixed point. And okay, so it need not be a fixed point. As we saw earlier, that the limit sets come in all different kinds of shapes. There was limit cycles, and then there was chaotic sets as well. And so my findings have mostly been in the chaotic sets in different systems, which I'll come to. But before that, I want to show you, tell you a little bit about the method that we have been using. So this method, it was originally developed by Professor York and his collaborators back then in 2001. And to understand this, I really want to emphasize, okay, the notion of escape time, first of all, that it's a property of a point. So let's say this is our region of interest that I have drawn in the black. And if we're talking about a point inside this box, the escape time of this point will be the number of iterations it takes for the point to escape out of this box. So hopefully you can picture that, this point is going to get iterated onto this slightly light blue point. I hope you can see it. And then in the next iteration, it will go to this point, and the next iteration will go to this point, this, and then this, and then eventually it will flow out. So the notion of escape time will become important in order to understand this algorithm. So just keep that in mind. So I get rid of all the clutter and zoom in on the region of interest. And this is really the crux of the algorithm. If you believe me, I've literally copy pasted it from the code that I wrote, although the 300 lines of code that I wrote. Well, not really, but yeah. So we start off inside our, so region of interest, firstly, we draw around our unstable limit set. Now, there is no real way of predicting where our unstable limit set is going to be, but if you can make a good prediction, then it's good. You'll, this algorithm will take you there. And so the idea is to surround our unstable limit set with the region of interest. And we start off with a point there, and we set a threshold first. our threshold is that, we'll only select points with an escape time of greater than or equals to 5. And using this, we'll generate a numerical trajectory inside the invariant set or the limit set. So we start off with a point. We check if its minimum, if its escape time is greater than our minimum required escape time. In this case, I have chosen the minimum escape time to be 5, and I see that the next 5 iterations of this point are still inside our region of interest. So I take this as a point of our stagger and step trajectory. Then I take a step to the next point, and I check if its next 5 iterations are inside my region of interest or not, and if they are, I accept it as a point. So this is the step part of the stagger and step algorithm. So every time you have a point with a acceptable escape time, you take a step, and when it's not, like the very next point here in this trajectory, I have to stagger. I have to stagger to a point from here which has a acceptable escape time for me. So again, I keep stepping on the same trajectory if the escape time remains good enough, and then I stagger like a horse in a chessboard probably if the escape time is not good enough for me. So the idea is really to keep high enough escape time. And you can sort of picture this as a feedback control algorithm, that I'm trying to see what the feedback, or here the feedback would be the escape time of the point. And I'm trying to see what is the feedback, and I'm trying to adjust according to that feedback. And the idea is to avoid the unstable manifold that I mentioned earlier. So I'm trying to stay away from the unstable manifold, and I'm trying to ride the flow along the stable manifold. And using this, hopefully you can see that I'll eventually converge onto, or like inside the unstable limit set. So are there any questions till now? Perfect. So now I'll move on to showing you our results. And the first result I want to show you is related to again, coming back to the pendulum. This is now a forced damped pendulum. And so in addition to having a damping, I also have an external force system. Now, because I have an external forcing, my dynamical variables are not just position and velocity as they would be in a usual pendulum. Because I'm adding energy to the system as well, it becomes a 3-dimensional phase space then. And so really what I have to do is see this after a particular interval. So like I start off at t equals to 0, then I see how the phase space looks like. Phase space, by phase space I mean x versus v, how that plot looks like after t equals to 2 pi. That's the period of the damping. And then after 4 pi, and then after 6 pi. So every multiple of 2 pi. That's called a Poincare return map or a stroboscopic map. And that's how we get all the plots that you'll see. And what you see here is how under this map the phase space would look like. And in pink you see, okay, so first of all, these 2 points that I've plotted here, the blue point and the pink point, they are the fixed point attractors of the system. There's only 2 fixed point attractors here in the system. And in the blue, you see the basin of attraction of this pink point. And in the pink, you see the basin of attraction of this blue point. So basin of attraction means that anywhere you start in this region, you'll eventually converge onto this point under the time 2 pi map that I mentioned. And then there is this boundary between these 2 basins, which is quite an interesting boundary. It's not a smooth boundary, it's a fractal boundary everywhere. So yeah, we'll come back to that. So these are the 3 saddles that there are three saddles I mentioned because I don't know if you can make out the different colors, but this is red and this is black and this is blue. So there's three saddles that I want to show you in this forced damp pendulum phase space that we have obtained. And the first one is the saddles embedded inside the basins of attraction. So this is the first basin of attraction, and there is a. So I have plotted two saddles here because they are essentially of the same type. I initially labeled them as different, but yeah, they are two different sets. They are two different saddles, but the type of saddle is similar in the sense that they are inside the basins of attraction of these attractors. And so you can notice that, by the way, you can ignore the yellow part for now. So you can notice that this shape, this saddle is inside the pink basin of attraction, and this is inside the blue basin of attraction. And yeah, if I get rid of all the clutter, this is how the saddles look like. And these shapes, they have very, interesting connectedness between them, or like an interesting behavior they show. And through testing we realize that, okay, so just remember this shape. If I go back to the previous slide, yeah, just remember the shape of this saddle, and this kind of forms like a, a two cycle here. You know, this shape gets mapped onto this shape, and then this shape on the in the next 2 pi it gets mapped on the this shape. And to show you schematically, this is how it looks like. So you can see that I've tried to draw a rough diagram of the right part of this bottom saddle, and this gets mapped onto the left part by getting stretched out like this, and then it comes back, gets smudged, and kind of becomes like that. So yeah, so this they have a nice back and forth, and the same happens for the top saddle as well, and they have a nice back and forth between them. So this is the first type of saddle that that we obtained that I wanted to show to you. The second type is perhaps more interesting, at least to me. That is the saddle on the boundary between the two basins. Now you see the points on the boundary, they have an inherent instability built into them if you think about it. Because if you are right on the boundary between two basins, either way you go, you're going to go away from the boundary because you're in the basin of attraction. So eventually you'll have to end up on one of the fixed points, right? So if you're on the boundary, there is an inherent unstable direction to move to. But what if you are to exactly start on the boundary? What will be your limit set then? The answer is this, at least in this case, this saddle that we obtain is the limit set of the boundary points. So in this sense, you can think that the unstable manifold of this saddle is the basins, and the stable manifold is the entirety of the boundary. If you remember the damped pendulum example. So yeah, again, getting rid of all the clutter, this is how the shape looks like. And the next image that I want to show you is my favorite out of the three. And this is going back to the Lorentz system. A little bit of the background on the Lorentz. We saw the trajectory that I plotted earlier. That was for a particular parameter value, and the parameter that I'm talking about is called rho or R. It's related to the Reynolds number of the flow. So the Lorentz system originally was supposed to model weather, right? And there was some, I think there were three parameters that were there in the system, and this specific parameter was related to the Reynolds number of the flow. And at R equals to 28, in the original paper, Lorentz plotted that beautiful butterfly shape, and that's when he analyzed that. But since the 1970s, it has been known that different behaviors are shown for different values of this parameter. So, for instance, if we are at for R greater than 13.926, we have the chaotic orbit still existing, but it will not be an attractor. it'll be a saddle. So before R equals to 13.926, there is no chaotic attractor even in the phase space. There's just 3 fixed points. And after 13.926, the chaotic attractors, so the chaotic set as a saddle starts to exist, and the fixed points are still there. And after 24.06, the chaotic orbit, it becomes a global attractor. So 28 is greater than 24.06, and that's why we see that kind of a spiral behavior, or like that interesting behavior for 28. And there is this parameter region then between 13.926 and 24.06, that the chaotic, as I said, the chaotic orbit is still present, but it's present as a saddle, as an unstable set. And so this is what we wanted to obtain. So we tried to run the stagger and step algorithm for these parameter values. So R equals 18. By the way, the rest of the parameter values, they are the same as the original Lorentz paper. And we just tweak the Reynolds number parameter to be between these limits. And we obtained a plot which I want to show to you in its 3-dimensional glory. Is it visible? Okay. So as you can see, it has that shape of a butterfly, as is there in the chaotic attractor as well. So I want to point out that stagger and step algorithm gives you a trajectory on the chaotic set, and it doesn't give you the entire chaotic set. So keeping that in mind, as you can see, this has that characteristic butterfly-like shape of the Lorentz attractor, but yeah, we are talking about a saddle here. It's an unstable set. And if I just zoom into one of these wings of the butterfly, zoom in a little more, maybe a little more, you can see this shape, which has this sort of the cell. You can sort of see that there is a cell similarity in this object. If you cut this object through the middle like that and see where the curves intersect, you will hopefully see that this will be like a middle thirds Cantor set, right? Or a middle alpha Cantor set. I don't know. You can tell me the value of alpha. It looks kind of like 1/3 to me. But yeah, so there is this big gap in the middle. The idea is that there is this big gap in the middle, and then there is these 2 smaller gaps, and then smaller and smaller gaps surrounding it. And there is a cell similarity in this object. So if I zoom into one of these arms, if I'm allowed to do so, hopefully it doesn't crash. You can sort of see that I get the object back, right? So hopefully through this presentation, I have been able to convince you that the unstable limit sets, they are also interesting objects to look. There are some interesting objects to look at when we study unstable limit sets as well. And we need to study them in order to get the graphs of the dynamical system, of course, but they are also important just as a completeness standpoint. Like if you want to study the dynamical system in its complete glory. So yeah, I think that'll be it from my side. And thank you very much. Yes. No?
Escape time depends on the domain.
Right, yes. The escape time will depend on the region of interest that we have.
Yeah. So is there any study between the time to escape from a domain and the nature of the domain?
No, there has not been any study. In fact, in many of our runs, I had to scramble through myself by trial and error that, what is going to be the right escape time. And choosing the right escape time usually took longer than the simulation itself. So, yeah, that has been that if there is studies on that, it will greatly help to run these. Yeah.
Any other questions?
Yeah, sure.
So, so there is some kind of stability to attend online lectures of Cedric Milan, Lambda Dam.
Okay.
So he says that there is a kind of stability, not for individual participants and its workings, but on the whole, there is an average that becomes stable in the long run. Statistical average. We don't bother about stress. For you, stability is a very restricted sense in terms of the factors, points,
Right.
response, and so on. But other than that, if you look at it as a whole, as a there is a statistical average.
Okay.
Stability in the past will come to this. That's that average.
Right.
Cedric Milan is the peace medalist.
Okay. So is that the does that happen for
I don't know. I mean,
this?
I am this layman's question.
Okay. Okay. Yeah, I'm not. I'm sorry. I'm not aware of those that claim. So yeah.
So thank you, Chirag, for the enlightening lecture. Thank you.
Okay. I'd also like to take a moment to thank all the organizers for calling me here, giving me a chance, and taking such good care of me. Yeah. Thank you.
May I invite Dr. Vinod Kumar PB to hand over the memento to Dr. Chirag Advani. Yes, yes.
Next plenary talk by Professor K.D. Joshi will start at 10 o'clock.
Professor K.D. Joshi to lecture on glimpses of data science. Thank you, sir.
Shall I keep it here in this pocket or? Ah, yes, yes. Shall we begin? Okay, I'm grateful to the organizers for inviting me for this talk, despite the fact that my expertise in this field is almost next to nothing. So I tried to dissuade them, but they insisted. And then they said, you have to motivate the students, the audience. It's not that you talk about a particular problem in data science or anything, but why it is worthwhile and especially what are its connections with mathematics, because that is the subject most of us are working in. So where does data science fit in all this scenario? Now, okay. Yeah, if you can enlarge it a little bit. Yeah, see, the best caption on data, I don't know who said this, was it Dhirubhai Ambani or somebody who had a very keen, whoever it is, but this is so true. Today, people are just fighting to get data because once you have data, you can do so many things. How to do them, that's a different matter. But first of all, you have to have a huge data. So remember, again, this is not my own advice, but the advice given by people who generally work in this. They say that be careful when you click on any attachment, because what the attachment is promising, that may not come true. But what will definitely come true is that you will be in their data field. And that is permanent. You can change your password and many other things, but once you are in their data list or repertoire, then it is like they can rule you. Not in the sense that they can grab your hand, but all the time they will be sending you messages. Even here, while coming here, the moment I booked my ticket to this place, I started getting messages like how beautiful Kerala is and what a great experience it is to be in Kerala. I never told anybody that I'm going to Kerala, but from the ticket they knew that I'm going to Kerala. So that's how things operate. They have operate in a very subtle way. And everybody actually, not just a mathematician, should be aware of the power as well as the possible misuse, like atomic energy. It can be used for good purposes, and actually it is. We are tapping the fruits of it. But it can also create an atom bomb which can kill thousands of people. So with data, every now and then you must be reading newspaper or stories that somebody was defrauded for 15 lakhs of rupees just because he happened to click on something. So why does that happen and how can it be prevented? So next page. So here are some general problems. Like I said, I'm not an expert on data science, but these are generalities. what do you do? First of all, data collection. Now, that is more a matter of conducting surveys or like, as I was just saying, espionage. That means without your knowing that you are adding to somebody's data, you are doing it by clicking on some link or something. But so sometimes by legitimate means, sometimes by illegitimate means. But data collection is a fact. I mean, it's a necessity. Without adequate data, you won't be able to do anything. A huge data is needed for many things. Then, how to store this data? That is more a problem of logistics. It depends on the purpose for which you want to store it. So later on, you want to retrieve it, say data retrieval. So these two are actually related. Where is the cue gun? This is the one? See, do I have to hold it? See, this data storage and data retrieval, they sort of go hand in hand, depending on what are your needs, for what purpose you will need to retrieve the data. It will be stored very much like this is common sense. I mean, depending on which books I'll need, with what degree of frequency, I arrange my books in my library. Like on the top part of the shelf, I keep books that are constantly needed. And somewhere at the back, I keep books that are needed not so frequently. So here also, data. So there is not much for me to add to it. Even if I had the expertise, I wouldn't be able to do that. So what are the, see that at the end, okay. See, mathematics enters mainly 3, 5, and 6. So that is data processing. It's not working here. It is working here, but no, it's working here.
Not working TV, only project.
Okay. Maybe in that case, I'll focus on this. So, yeah, data processing. Let us go back. Data processing. Now, there is a huge data, and from that, you have to pick some relevant data and then do something, whatever you want to do with that data. So that is called data processing. What you want to do, that will depend on the application you have in mind. For example, if you are someone who is trying to promote a product, then as I was just saying, you will have to process the data in such a way that people who are headed for Kerala will come on your list. There will be a huge data of travelers, but you will pick those who are going to Kerala so that you can advertise advertisements about Kerala. So that is data processing. Data retrieval we talked about. Data transmission, this is an important problem. Data transmission means you have got something with you. Now, in the past, you will send somebody physically to give the data to somebody or a part of it to somebody. Now that's too slow in today's times. So you send the data electronically. Now for that, you have to convert the data in terms of binary code, usually binary code, there can be other codes. And then you have to send the coded word or what is called a message that goes across to the other party. So basically the idea is simple, but how do you do that? We'll come to that later. There is a challenge in it. It's not as simple as just asking somebody, okay, give this letter to so and so. It's not that easy. So there is a science of that is called coding and decoding. We'll talk about it later. Data transmission and finally, of course, data security. I mean, if data is gold, naturally people will try to steal it. That is very common. If you cannot get data by legitimate means, you do plagiarism. You try to break open somebody's data, hacking, that is the word for it. So how to guard against that? That is another science which has come very recently, because till now, there was physical storage, and then protecting it means putting some armed security there, the usual thing. But data security is a different thing. It has no physical model that you can put in a room and then constantly somebody can protect it. It's not like that. So for mathematics, especially data processing, data transmission, and data security, these are the major challenges. Next, please. Page 3. So let's come to data processing. What are the 3 problems in data processing? First, given a raw data, you must see if there is pattern recognition means. Do you see any pattern? For example, if you are given a list of tourists traveling all over the world, is it that every 10th person is going to Kerala? If so, you can be more efficient, because then you focus only on these persons without actually verifying if somebody is going to Kerala or not. Just pick up the numbers which are multiples of 10 and do that. But first you have to see that pattern. If it works, then you harvest the outcome. But how to get the pattern? We'll see examples of this. Then design of algorithms. See, for data processing, you need efficient algorithms. Because again, this data is in electronic form, in the form of bits, and you want to do some manipulation to it. Either you want to sort it, you want to store it. So for that, you need algorithms. Algorithm means definite processes. Now, how to get good algorithms? Well, that is an important problem, but then that all depends. What is a good algorithm, or how to design an algorithm for a particular purpose will depend on that purpose. Okay, like for example, take the problem of sorting. You take, let us say you are playing cards. So you take one card, you put it. Then you take the next card. Either you put it on this side or this side. And that way, simple comparison will give you. But in this, the cards are at a random order. The deck is shuffled and the cards will come in any random order. Whereas in other places, like suppose you go to a library, now some of the books are misplaced. But here the assumption is that very few books are misplaced, unless somebody is deliberately playing a mischief. Then you can design a better algorithm. Instead of taking every book and then putting it, you can take a random search, or you can save time by taking advantage of the fact that already the data is mostly in order. So that is a different algorithm. An algorithm which works for one kind of data may not be the best one for the other one. So design of algorithms is relatively outside the domain of mathematics. But then analysis of algorithms. Analysis, what it means will come a little later. Analysis of an algorithm means deciding beforehand how efficient it is. There is the empirical test of running an algorithm and trying, counting how much time it took to process. But that is, anyway, that is a practical method. Ultimately, it has to be tried also. But before that, how do we decide that something is a good algorithm or not? Now, mathematics enters primarily in pattern recognition and three. So we'll study these two. And design of algorithms, I'll not do much because it depends on the problem and what particular type of data you are handling under that problem. So I'll not say, next page, please. Yeah. Now, here is a pattern recognition problem. And this is a classic problem. First, what is the number of partitions of an integer? First of all, what is a partition? I think here it is too small for many of you. So I'll read it out. A partition of an integer means you really partition it so that the parts add to the given integer. Okay. Now, suppose there is a 3-element set and I can partition it with 2 elements in one class, 1 element in the other. Or I can put 1 element in the first class and 2. But in partition, these are considered equivalent. So in a partition, what matters is the sizes of the parts. And parts of the same size can be anywhere. So merely ordering the parts doesn't change the partition. That is why it is customary to write a partition so that there is a descending order of size. You can put it in ascending order also if you like, that is up to you. But the convention is that you always take a descending order. Now, partitions arise in many real life problems as well as mathematical problems. In my book on discrete structures, I have given a problem. Sometimes you have restricted partitions. Like you want to send an envelope. And let us say the envelope, the post charges 2 rupees or whatever amount you decide, 20 rupees, let us say. And the stamps available are of the denominations, let us say 1 rupee, 2 rupee, 5 rupee, and 10 rupees. Or you can say even 20 rupees for that matter. So, in how many ways can you make a postage? Well, that is exactly the problem of the number of partitions of 20. So that the part sizes are either 1, 2, 5, 10 or 20. Like our wallet notes, you see, they come with that denomination. And in how many ways can you make that? So that is a partition problem. It is a variation of it. It is called restricted partition problem because you are restricting the part sizes. Now, in my book, I have given this as a postage problem and I have made a comment. The reader may wonder, why on earth would anybody want to count how many possible ways there are to affix a 20 rupee postage? When in reality, any one of them is as good as the other. The post office is not going to reject. Oh, no, you should put a single stamp of 20 rupees. 2 stamps of 10 rupees will not do. There are people who take pride, who feel they are doing something great. And then they give some weird similes. Suppose my daughter is of marriageable age and she is, let us say, 18, just turned 18. So find a young man of 20. Now, are you going to send me 2 boys of 10 each? That's ridiculous. Well, yes, that is ridiculous. But putting 2 10 rupee stamps on the postage is as good as 1 single 20 rupee stamp. So in real life, such questions might look silly, but then after all, if it is all hypothetical, I can give a hypothetical answer to that. Let us say in the old times where espionage was done very naively because there were no other means. So secret codes had to be devised. So what one spy does is he sends an envelope with 20 rupees stamps on it Now, if you open that envelope, then the message is Aunt Dorothy has arrived safely or something. So nothing cryptic about it. And best wishes for your children and that type of thing. Where is the real message? In the combination of the stamps used. So the person who receives it is more interested what stamps have been put. And then how many different messages can be sent. That is equivalent to asking what is the number of partitions. Or as a mathematical example, in group theory, you know that when are two permutations conjugate of each other? When they have the same cycle structure. And any two cycles commute with each other because they're disjoint. So you write the cycles in a descending order of length, and that will give you one permutation. And any other permutation with the same cycle structure will be conjugate. So what is the number of conjugacy classes in the entire permutation group of n factorial permutations? Well, that is exactly the partition, P of n. P of n denotes the P of n is the number of partitions. Here I am not taking restricted partitions, all partitions. So let us see, there is only one way to partition it, just one. For 2, there are two ways. Either you can take a single piece of 2 or you can take 1 and 1. Now that is common sense, of course, nothing great. 3, 2 plus 1, 1 plus 1 plus 1. So you might think that always P of n is the same as n. P of 2 is 2. P of 3 is 3. So what about P of 4? You expect. So you have got a pattern already. P of n is n. But then let us try if it works. So take the next one. N is 4 and the partitions are either 4, 3 plus 1, 2 plus 2, 2 plus 1 plus 1 and all ones. So 5 partitions. So P of n is not equal to n. Life is not so easy that although it appears when you look at only the first 3 examples, you might think that yes, I got a formula for the number of partitions. That is wrong. And in fact, see this P of 1, 2, 3, but then P of 4 is 5 and P of 5 is 7. So again, it's not like n plus 1. Okay, the next one. Now, here the values of n and the corresponding values of Pn are given up to 50 and then some 99, etc. So you can see it increases very rapidly. P of n grows not as rapidly as n factorial, of course, but still fairly rapidly. And in fact, so far nobody has been able to get a formula for P of n. People have tried it, but no, it's not like n cube minus e raised to n or something. No. Such a formula, at least to my knowledge and probably to anybody's knowledge. If somebody comes up with a succinct formula, that will be quite a lot. That will be a great discovery. So, can you recognize any pattern here? See, n is 11, 6, 11, 15, 22, 23. My God. The only sure thing is they are increasing numbers. Beyond that, you can't make out anything. It's as if some random numbers are taken and they are put in an increasing order and listed in the column of Pn. So, is there any pattern? Well, people will say, no, you can't. I mean, giving a formula for Pn is great, that nobody can do. But at least, can you say that if n is something, then P of n has some property? Can you at least say that? If so, then you have discovered a pattern. So people tried this. But then, the next page. See, there was one person who discovered that if n is of the form a multiple of 5 minus 1, see that 4, that is 5 minus 1, and then see that underlined 5, that means the number of partitions is a multiple of 5. Then the next one is 9, which is also 1 less than a multiple of 5, and Pn is the number of partitions, 30. See that? 14 and 135, 19 and 490. Every time it is divisible by 5. If n is 1 less than a multiple of 5, or people sophisticatedly see, if n is congruent to 4 modulo 5 or minus 1 modulo 5, then P of n is divisible by 5. Okay? So that is, now you must be knowing who discovered this, but in case you didn't, there is the next page. See, it is this person. At his time, there were no search engines, nothing. Just raw data was available. And by looking at this selected, because after all, there are infinitely many integers. So trying to guess a pattern by seeing a few examples, only Ramanujan can do that. That is the genius of Ramanujan. Just as on the cricket field, there is Tendulkar. I am not much of a knowledgeable person in cricket, but I heard some experts saying, what is really so great about Tendulkar? What? He scores centuries, or when he gets to 90, then he starts sort of stumbling, or no, the person who knows really what cricket is, he said that for any batsman, the fielding is usually arranged so that there will not be any gap. That is the challenge. And a good captain, he knows what are the habits of this batsman, and he will arrange the field according to that. So there will not be any gap, to a layman at least, and even to an expert batsman, but not for Tendulkar. Tendulkar will always find some gap between what are the technical terms, mid-on and deep leg or whatever it is. And then he will hit the ball there. But that is the genius. That is why he is Bharat Ratna. Whereas there are many good batsmen, no doubt. Tendulkar was not the only great batsman, anybody. But what makes him unique is this ability to see the gap. Similarly, what makes Ramanujan unique is that he was able to see these congruences. If n plus 1 is divisible by 5, that means if n is 1 less than a multiple of 5, then P of n is also divisible by 5. Similarly, if n is 2 less than a multiple of 7, then P of n is that back screen. Let us verify the second one, back screen, back page. See this, if n is 2 less than a multiple of 5, that is 5, then P of n is divisible by 7. The next is 12. And yes, this is divisible by 7. Then the next is 19. And yes, this is divisible by. But again, no human being can see infinitely many multiples. And there is no regularity. There is no formula for P of n. That is why discovering such patterns has its own value. So, Ramanujan not only discovered this for a few values, he proved this. And as I said, I am not an expert on data science, but I would like to learn from those who are experts. My question is simple. Ramanujan proved this, that for every multiple of 5, for every integer which is 1 less than a multiple of 5, the number of partitions is divisible by 5. He proved it. So there are infinitely many positive integers, and he proved something in general. Whether chatbot or these other AI, artificial intelligence devices can do that, that is my question. Surely, if you give them a finite set, they will come up with some pattern which holds for that finite set. But will they be able to recognize that this holds for all? Because giving a proof is a different thing. That is really not a part of data science. Data science will help you discover a pattern. What are the algorithms for pattern recognition? It is like guessing something and then verifying your guess. Well, people have been doing that even before the modern inventions came. But now problem is more challenging because the data is huge. So by physically searching or calculating every piece of data, you will not be able to handle the whole data, even though it is finite. So I would like to know if, or let me tell you a much simpler problem. You give this one of these AI machines or whoever they are, you give them the definition of a prime number. And you ask them to list all primes. You ask them to list all even primes. You give the definition of an even number, you give them the definition of a prime, and list all even primes. That is my question. Will they be intelligent enough to understand that by definition, if something is even, it is divisible by 2, and then it is not a prime unless it is 2 itself. So this kind of very elementary reasoning which human being can do, can a machine do that? That is, well, as I said, I am not an expert. They can imitate human thinking, but this is not just donkey work where you are applying an algorithm. That inspiration, that number is 1 which is divisible by 2, then how can it be prime unless it is itself equal to 2? Now that I am not sure whether machines can do. Maybe later on, but then that will be quite a breakthrough. Okay, 2 pages later. So this is not very relevant, but this is a mathematical problem. And I thought it is worth remembering Ramanujan. So I dragged it into this. Now let us see. Our next question is analysis of an algorithm. Analysis means determination of, or let us say advanced determination of how long it will take to process a given piece of data. Sorting, for example. The efficiency of a sorting problem is you are given n objects. They can be cards in a pack, or they can be books, or they can be entries in a telephone directory, whatever it is. Now, how long will it take to put them in order? That is the question. But now the trouble is, as I said, it will all depend on what your piece of data is. If your data is already sorted, then it will not take much time because you will not do any shuffling. Just ace of spades, then ace of hearts. Then they are in descending order, luckily, already. So we go by what is worst case performance among all pieces of data which have a given size. What is the worst that can happen? Okay, so this is a sort of pessimistic or what you can say too cautionary model. So that if you know the worst case performance, if you know that even in the worst case it will not take more than 1 minute, then you are safe. You have found that 1 minute is a safe margin. But that is misleading. Many times things are not so bad, and then you come to average performance. Average performance. And this is again a very elusive term. What is the average height? Well, on what class? That is the question. Are you talking of average height of people in India or people in Norway or what? Or people in those Africa, pygmies? So that is a very elusive term. What is? It all depends on which class you are taking it. And then again, even on the same class, what is the probability distribution of picking the data? If you are going to pick some data more frequently and apply the algorithm, then that should count more in taking the average. So average really means weighted average in this case. You have to give weightage depending on the probability of picking up that piece of data. Let us see. Yeah, I'm halfway through, I guess. So these are important problems, but asymptotic performance. Now this is something I think most of you here will know, but in case you don't, where do you first encounter that term asymptote? Where do you see that person, asymptote? Do you remember? Well, ask your children. They will, if they are appearing for JEE or something, surely there will be a problem about asymptotes. So it is a geometric thing. It is a geometric concept. It is defined as tangent at infinity sometimes. For ordinary tangents, the point of contact is finite. For an asymptote, the tangent keeps going close and close. So the next page, please. See this familiar one branch of hyperbola, another branch. Now for large values of x, this actual curve and its asymptote, which is this straight line, they come so close to each other. Because then the dominating term, when x is dominating, you can write the equation after dividing this by x, that for a fixed a by x will be negligible if x is large. And that is why asymptote is a approximation which holds for large values. Okay? For small values, the difference between a point on the hyperbola and the corresponding point on the line, that is quite measurable. It's not small. So in asymptotic estimation, you worry what will happen in the longer term. That is when the data size is large. And that is why it is more relevant today. Till a few years ago, the data sizes could not exceed a certain limit, which was humanly decided. But now the data can be huge, so you have to worry about it. There may be some algorithms which are perfectly good for small size data or medium size data, but asymptotically they may not be so good, or vice versa. There might be some algorithms whose asymptotic performance is quite good. So that is needed because of large size. So next page, please. Next page. So for this, you need to estimate some commonly occurring numbers. So this is not directly relevant to the asymptotes of a hyperbola, but these numbers, it is called the nth harmonic number, the sum of the reciprocals of the first n integers, that is h sub n. And from a number theory point also, there is a lot to be said about harmonic numbers. When are they integers and that kind of thing. And most of the time they are not integers. They are rational numbers, no doubt. But for large n, is there some convenient function which is close to nth harmonic number, but which I can evaluate easily? Or do I have to go through the jazz of adding 1 plus 1/2 plus 1/3 up to 1 by 10,000? No, that should not have to be the case. So this is a very elementary technique in calculus. See, this is the graph of y equals 1 upon x, because the area under this graph is precisely the logarithm that anybody knows. Now you approximate this area under the graph by these areas. So this is the actual area of the first rectangle. This is the area under the graph. So this will give you, if you calculate the shaded area, the total shaded area grows. But you can see that after some time, the increase is very, very small. As a result, even though this ln is bigger than h sub n minus 1, as you see from here, the difference is not very big. It is bounded above by 1. So it is tending to some definite limit, this difference hn minus ln or hn1 minus ln, mean the same thing. And that is some fixed number between 0 and 1. That is called the Euler constant gamma. And its value is something like 0.57 or something. But anyway, in asymptotic estimation, what matters is for large n, the nth harmonic number h sub n is very nearly equal to log of n. And that is good enough because there are easy tables of log of n available. Whereas calculating h sub n by actually summing up 1 up to 1 upon n, that's going to be a tedious job. The next page. A bigger version of this is the Stirling approximation to n factorial. Because if you ask which numerical function, the number theory function, comes most frequently in combinatorial problems or in discrete mathematics, it is factorial function. Where do you first encounter factorial function? Of course, people might have different experiences, but one very common is the number of ways or the number of permutations of n symbols. Well, that is n factorial. But if you take number of combinations of say 3 things out of 5, then it is 5 factorial divided by 3 factorial into 2 factorial. Now we can quickly cancel the common factors and say this is 10. Okay, fine. But suppose you want to calculate in how many ways can you choose, let us say, 70 objects from a collection of 100 objects. Now the answer will be 100 factorial divided by 70 factorial into 30 factorial. Now ordinary calculators will not be able to handle this. So you need Stirling approximation. Well, anyway, this is a sample of how mathematical methods are applicable. So this time, in the last example for log n, we used these areas below the graph. Here also we use these areas below the graph. This is in fact very common. This is the trapezoidal approximation to an integral. And you can do it for any definite integral. You can you can partition the interval a to b into n equal parts. They don't have to be equal, but it is convenient. And then you approximately take the area below that portion as if it is a trapezium. So that is what is done here. Now here the curve log x, y equals log x, it is what is called concave downwards. You can check from its second derivative. Okay, maybe, shall I show it? See this? So what is dy by dx? Well, it is 1 upon x. And what is the second derivative? So it is always negative. That means the curve will lie above, above chord. If you take any 2 points, then the chord joining those 2 points, the chord joining those 2 points will lie below the graph. As a result, the difference here is always positive, and again, as n increases, it increases. But once again, the next page, it doesn't increase that much. First of all, you realize that if you let an be the log of n factorial, that's much easier to handle, because logarithm has this property that log of a product is the sum of the logs. So instead of n factorial, you take the logs and add them. And then you can apply this method of calculus. So you get that Bn is the area under this log x function. Tn is the trapezoidal approximation. And the areas of trapezoids are very easy to find. The previous page, please. The previous page. See, these are the trapezoids here. So what is the height? F of 3 plus f of 4 divided by 2 into this width. The width is 1. So by merely doing some arithmetic, you get the next page. So you get that the area of this trapezius is this, and that is n minus 1/2 of log n. That's very sheer calculation, nothing is. So ultimately what you get is that this trapezoidal areas are almost as big as this area under the graph. And then you get the approximation in the logarithmic form. Taking exponentials, you get n factorial is n raised to n times n raised to 1/2 divided by e raised to n. So that is how big n factorial is. The exact value of this limit as n tends to infinity, that can be obtained. It is root 2 pi, but that is not very crucial. It's some fixed number. So this is where mathematics is getting some challenges posed by data sciences. What is the asymptotic performance of algorithms? Not performance on some familiar finite data, but data science, because of advances in data collection, the data collected is so huge that you must take into account what is the asymptotic performance of an algorithm. Okay, let us see how much time we have. Well, about 10 minutes, I guess. So the next page. Now here is an application of that Stirling approximation to that sorting has come twice, sorting problem. So in a typical sorting problem, what is the data? You are given numbers, let us say. They are given in random order. And sorting means putting them in an ascending order or descending order, whatever you like. That means what? That means finding a permutation of these n symbols. What is that? Okay, is it coming here? Yeah. So, see, there are n factorial permutations. You have a data to start with. Now, which permutation will give me the entries in an ascending order? That will depend on the data itself. But In all, there are n factorial possible permutations. Now, every time you take a new piece of data, you are comparing it with each of the earlier pieces you have picked. So, each comparison is like a binary test. Given the new card, is it bigger than this card, the last card? If so, keep it at the end. Why are you unnecessarily comparing it with the earlier cards? You already know that. But it might happen that the new card that you are picking is smaller than the last card, even smaller than the second one, and fits somewhere there. Then you put it there. So, with two-way testing, each comparison gives you two possible outcomes. This number is either bigger than this number or less than that number. So, how many comparisons will you need? That is the questions. And here we are not talking of by stroke of luck. By stroke of luck, you may not have to do any shuffling. But that is accidental. If it is a bad day, then you may have to do all comparisons. By the way, there is a puzzle, you might have heard it. I think he was a famous mathematician, not more of a physicist, but in the good old British days. That Tripos exam, that was a very coveted exam. People used to fight, bright boys used to fight for topping that exam. So, this fellow, Kelvin, I think, Lord Kelvin, he was so sure when he was a student that he will top the list. He was absolutely sure. But he was curious to know who is the second. So he asked his servant, because in those days, results were not declared online. You had to go physically to that Cambridge notice board and read the results. So he asked his servant, okay, go and find out who has come second. So after some time, the servant comes and says, it is you, sir. My God, that fellow, I don't know what was his reaction. But then to find out who is the first one, he had to send somebody again. Now, remember this. Here we are talking of knowing who is the second. But if you are deciding who is the second person by actually doing some algorithm, by actually doing some comparison, you cannot do it unless you have also found who is the first one. Why? It is impossible. It is possible to know who is the second one without knowing who is the first one. In fact, that's what happened. But if you want to find out who is the second one, there is no way without finding out who is the first one. Why? Well, that is a problem even in discrete mathematics. See, the very fact that somebody is second one means somebody has defeated him earlier. Right? But only one person has defeated him. So you take that person and read his history. If you are finding, then you already know what were the outcomes of various games, various comparisons. So you will come to know who is the topper. Without knowing the topper, you will not be able to tell who is the next one. So that is another problem. But here coming to sorting, observations as theta varies over the set of all permutations, there are n factorial permutations. Now each comparison has two possible answers that we know. So in k comparisons, next page, the set gets divided into 2 raised to k subsets because it's like cutting a piece of cake. You first divide it into 2, then the second comparison will divide it into 4, and so on. You go on dividing until all pieces have either one element or no element. Because then you know, then you have sorted all pieces. So in order to finish this process by this binary method, how many comparisons will be needed? Well, it is the least integer such that 2 raised to k is bigger than n factorial. In the worst case, you might need that many. So if you take logs of both the sides, then it is this k times log 2, that is the log of 2 raised to k, and then Stirling approximation for log n factorial. Now, once again, what is the asymptotic here? Out of these two terms, which vary, one is a constant, forget about it, but which is the dominating term? N log n, 1/2 log n, or n? Well, obviously n log n. As compared with n log n, n is negligible. And as compared with n, log n is negligible. So the dominating term is n log n. So that is how you estimate the efficiency of an algorithm for large data. That is asymptotic estimation. Okay, I suppose I'm almost now out of the next page. I'll just briefly talk about this data transmission. How do you transmit a data from one end to another end? Let me give you a real life example, again in the form of a hypothetical old time story. So let us see, let us suppose there are 3 sisters and their names are Lena, Meera, and then Geeta. Now, Prince Charming is visiting the family, and naturally, all these 3, they try their best to win his love and attention. So eventually, he falls for one of them. But it's not like modern times that you suddenly go and say that, I love you. He's shy, so he leaves without telling anything. But then afterwards, he sends a telegram. Okay? Now the telegram, unfortunately, fortunately, the message in the telegram is simple. I love you, that's all. But it is addressed to now let us assume Meena is not the name of the mother of these girls, because if that is the case and she opens and sees I love you, immediately the whole thing is gone. So let us assume that there is nobody in the family with this name. So what has happened is the telegraph office has committed a mistake in sending the message. The intended message was one of these, Lina, Meera, and Geeta. The received message is Meena. So who do you think is the rightful addressee? It has to be one of these. Lina? Because you can see that the second letters match, even this matches this. Only difference is first letter. So she will say, obviously it's me. He went to say, send it to myself. But the telegraph office made a mistake. And instead of L there. But Meena will not give up. Meera will not give up. What will she say? Well, the first letter is correct, second is correct, third is correct, last is. So, if there was one mistake, it could be as well the fourth letter. What makes you think that the first one was the wrong letter? And Geeta, she is the unfortunate one, but she will say this, that, oh, this post office, this telegraph office, they make so many mistakes. So if they make a mistake, they could have made 2 mistakes. And so it's me. 2 letters have gone wrong, but it's me. So how do you resolve this? Then the parents intervene and they say, they curse themselves. Why did we give such closely resembling names for our daughters? If we had named them just short 5-letter names, but here I am giving one possibility. Let us say Kamal, Sudha, and Aditi. Okay. Now suppose the post office, the telegraph office makes a mistake and some letters are wrongly sent. So that the recipient now is a Vimal. Vimal. Now who is the rightful recipient? If Vimal is the person named on the telegram, who is out of these, who stands the best chance? Kamal. Because Kamal is close to Vimal. At least she can claim that 3 letters are common, which Sudha cannot claim or Aditi cannot claim. So you might say she has a better argument. Whereas if the telegram was addressed to Radha, then who is the rightful recipient? Sudha, because again the same reason. So here the problem is that the names are very closely resembling. Now let us introduce a metric D. D, that means the distance between 2 names. Let us say the names are of the same size. So define the distance between 2 names as the number of letters where they don't match. If they match, then the names are identical and the distance is 0. So what is the distance between Leena and Meera? Well, these two are different. So the distance is 2. Right? But what is the distance between Leena and Meena? That is 1. The distance between Meera and Meena, that is also 1. So that is where the problem is. The data or the coded messages, they are too close to each other. The distance between them is 2. If they were like this, what is the distance between Kamal and Sudha? Different. So the distance is 5. Here what is happening is layman's thinking. Suppose you have objects which are placed far away from each other. And let us say somebody gives you a slightly wrong address so that you land within a certain distance of one of these persons. Now, if the mistake is small, then you can tell who is the rightful recipient or who is the rightful person. So that is what is called error correcting codes. That means you, instead of Leena, Meera, Geeta, you take these code words. Or you can design longer code words so that the distance between any 2 of them is 7. If the distance between any 2 code words is 7, that means up to 3 errors will be tolerated. Because you take one code word, distort it by changing 2 or 3 letters. Still it will be farther from the other candidates. So how many errors can the code correct? Now you will say, why make mistakes then? Just be careful in sending messages? Well, these are not errors of the human type. These are not human errors. Why do these errors occur? See that? Problems. Main problem is errors, of course. Problem source is not human negligence, it is noise. And what is noise? It's not this loudspeakers type noise. There you can say, oh, it was so noisy. I didn't really hear whether it was Lina or Meena. Maybe I made a mistake. No, it is not this kind of noise. It is a noise which you cannot prevent. It arises because of the limitations of the communication channel. It is an electronic channel. And there is an element of randomness in the motion of electrons. So there is that principle of uncertainty. You can never tell where an electron is at a particular moment. There is a probability that it is here. So this noise is inevitable. And because of that noise, such errors occur. So the only solution we have is to take code words which are far away from each other, so that even if one or even two mistakes are committed, they can be detected and then you can correct them. So this is a problem in coding theory. In decoding, this doesn't arise because you have already received the message. Maybe it is a wrong message, but now there is no question of sending it again. So this leads to a theory of what is called error correcting codes. Now, what are the mathematical tools needed? One is finite fields, especially of characteristic 2. Because binary codes, they are codes over this alphabet. Okay, just slightly over time. So this is a big, interesting problem in coding theory. Now, coding theory is a separate branch of data processing. And the main problem is this: how to design codes which are able to correct a certain number of errors and which are not unnecessarily long either. Because the longer the codes, the more time it will take to transmit them. So that is a challenge. And as I said, the finite fields, they are the right, at least at present, they are the best sources to design such codes. Okay, I think the last page now. Last page. Here, I have absolutely no knowledge except to read newspaper items that somebody was defrauded and things like that. But this is coming under a new branch of mathematics called cryptography. Now, there are books on cryptography available. And they tackle this problem of how to design or how to encode the data so that it cannot be easily broken. How to give passwords so that they cannot be easily hacked. And the best source of passwords is primes. Primes. I'll give you two primes. Let us say 11 and 7. Then their product is very easy to obtain. Multiplying two primes or multiplying any two numbers, that is a mechanical process, it can be done. But if I give you the product of two primes, and I tell you it is the product of two primes, how to find those primes? Well, you say, first of all, is that number even? No. Then it is not divisible by 2. Is it divisible by 3? No. If not, try divisibility by 5, divisibility by 7. So you will keep on trying this. Eventually, you will be able to factorize that within after maybe 1 or 2 years, because that's how big primes are. The number of primes is infinite. By that time, the person might have changed his password so that cracking the code is no use now. So that is the best source of generating unbreakable, theoretically unbreakable codes. Random number generators are important in this because things have to appear random. If a sequence is random, then it is difficult to remember. If I give you the sequence, take the sequence 2, 4, 8, 16, 32, 64. What is the next term? 2, 4, 8, 16, 32, 64. What is the next term? 128. Because there is a pattern now. But if it is a random sequence, you cannot guess the next. So they are good source of generating safe, unbreakable codes, prime numbers, and again the multiplicative group of finite fields. Because you know that a multiplicative group of a finite field is cyclic. So finding the order of an element in the cyclic group of a field, that is a challenge. If you give that, that will be a good password. Well, anyway, as I said, I don't know much about these things. They have come very recently. But then for that matter, I don't know much about data science either. So my job was to motivate you. I hope you are motivated. If that is the case, I'll be happy. Okay, thank you so much.
Hello. Any questions from the audience?
Sir, I have a question. See, people talk about these issues like I'm here. Data validation.
Data?
Data validation, as the data starts streaming in, prior to doing any kind of processing, you have to validate and you have to assess the quality of the data also.
Yeah,
people normally
no,
because
quantity or
quality.
quality. Quality from what point of view?
That's it. That's the question. So we normally do it in terms of outliers or in terms of mean or variance or something like that. Other than that, is there any kind of quality definition for data?
It will depend on the purpose for which you are applying the data. So, like this sorting problem itself, if the data is almost well sorted already, then you will call it a good quality. But then that is because of a particular application. The same data may not look so good for somebody else. These are problems specific to a given application. So mathematics under them is the same, but the outcomes will be different. They will not be the same.
Okay, sir. Thank you.
Anybody else?
Sir, this depends on the current computational facility, current computer systems.
What is
Right?
it?
So if you have quantum computation reality, yeah, quantum computation
Sorry, I know
reality.
nothing about that.
So
Now quantum computation, I only read. I have no idea of how it is affected. Or yeah, but it's supposedly faster than the previous methods. Right? Quantum computation. No, I have no idea. I know quantum physics, but I mean what it is basically, but the photons and that type of thing.
yeah.
Quantum, no.
So most of the problems which are very complex becomes polynomial kind of thing, and so.
Yeah, but this is for me also. It is only what I casually read. No,
Okay.
I have not studied that
Thank you.
subject. Anybody
Any
else?
more questions? So otherwise, let us thank Professor Joshi for a very enlightening talk of the mathematics behind data science, which is equally applicable to other places also. So thank you, sir, for an excellent.
May I request Narayan Nambudri sir to hand over a memento to KD Joshi sir? Thank you, Narayan Namudri sir, for chairing the session. Now we will have a photo session. For that, I will request all of you to please assemble in front of this seminar hall. After that, we will have the tea break, and I request all of you to be back to this seminar hall at 11:30 a.m. after the tea break. Thank you.
Welcome back, all of you, to the session. So now we have the honoring session. We honor our professors for inspiring, motivating, and guiding the generation of students. I welcome Vinod sir to give an introduction about the professors.
Welcome to Guru Vandanam. Acharya Devo Bhava. The word Guru is derived from the Sanskrit language and has a deep meaning. Gu stands for ignorance and Ru represents the radiance of knowledge that dispels the ignorance. Guru is one who dispels the darkness of ignorance in humanity and bestows knowledge. Saint Kyriakos Elias Chavara is the founder of Carmelite of Mary Immaculate, the Catholic congregation who managing this institution. Saint Kyriakos Elias Chavara was a Catholic priest, philosopher, and social reformer. He started one institution for Sanskrit studies at Mananam in 1846. Then to each parish, he attached an educational institution. Following the founder father, Rajagiri School of Engineering and Technology has the tradition of honoring gurus. It is a tradition of our country to respect gurus. In Indian tradition, a student-teacher relationship is considered to be very auspicious and respectable. Kerala Mathematical Association always stand in front to give due respect to all the teachers. As far as the mathematics community is concerned, 4 professors who served in 4 different institutions in India deserve to be called as the most sacred word guru for their dedication, guidance, hard work, research, teaching, and lifetime contributions to mathematics. Professor R. Vittal Rao, formerly of Indian Institute of Science, Professor V. Kannan, formerly of Central University of Hyderabad and presently at SRM University, Professor K.D. Joshi, formerly of Indian Institute of Technology, Bombay, Professor A. Krishnamurthy, formerly of Cochin University of Science and Technology and currently at Center for Research in Mathematics, CMS College. Their presence, lectures, words, and deeds have inspired many students, teachers, and researchers, not only in India, but all over the world. The students and teachers of mathematics of the whole nation will bowing their heads at the feet of these gurus, bless us and guide us. With blessings of Almighty and gurus, we wish to inform you that Rajagiri School of Engineering and Technology and Kerala Mathematical Association, this is the second episode of Guru Vandanam. We had the good fortune to honor Dr. K.S. Subramanian Naburipat, formerly of University of Kerala, Dr. R. Shivaramakrishnan, formerly of University of Calicut, Dr. T. Trivirkaman, formerly of Cochin University of Science and Technology, during the annual conference of Indian Mathematical Society in 2013 held here. For this function, may I request our dignitaries to occupy their seats on dais. Professor R. Vittal Rao, Professor V. Kannan, Professor K.D. Joshi, Professor A. Krishnamurthy, Director of Rajagiri School of Engineering and Technology, Reverend Father Dr. Jose Courier, CMI, Principal of Rajagiri School of Engineering and Technology, Professor Dr. P.S. Srijit, General Secretary of Kerala Mathematical Association, Dr. Paul Isaac. Ramachandra Ajar Vittal Rao, son of N. Ramachandra Ajar and Narmada Bai, was born in 1941 in Tamil Nadu. Professor R. Vittal Rao obtained his MSc degree in mathematics from Mysore University and his PhD degree in mathematics from Purdue University, United States of America. He was a faculty in the Department of Mathematics at the Indian Institute of Science, Bangalore, for more than 3 decades and retired in 2003 as professor and chairman of the Department of Mathematics. After his retirement, he was a consultant in the Department of Electronic System Engineering, Indian Institute of Science, until 2022. He has held positions in the Department of Civil and Hydraulic Engineering at IISc, Department of Computer Science and Automation at IISc, and Department of Mathematics at Indian Institute of Technology, Madras, as Senior Scientific Officer. For several years, he served as the coordinator of the High School Science Teachers Program of the Center for Continuing Education of IISc. He was also a guest faculty at Indian Institute of Management, Bangalore. He was visiting faculty at Purdue University and Iowa State University in USA. He was the recipient of the Jaya Jayant Award for his teaching excellence at IISc. His research contributions interests include analysis, function analysis, differential and integral equations, linear algebra and applications, combinatorics, and general applications of mathematics to engineering problems. It is very well known that his lectures are lucid, elegant, and inspiring. His lectures on linear algebra, mathematics for electrical engineers, and various other courses are popular in IISc, NPTEL platform, YouTube, and in several other platforms. His talks in various conferences have motivated many researchers. There is a famous quote, I quote, "If you cannot explain it simply, you don't understand it well enough." Quote ends. We realize the meaning of this quote in each and every lecture taken by him. Be it any complicated topics, after attending his lecture, it used to become crystal clear. He always starts with very simple theorems, concepts, and then build the whole idea based on it. Once the lecture got over, it used to strike us what we just learned starting from such a simple idea. He has visited Rajagiri School of Engineering and Technology many times. He has given lectures in many conferences organized by Kerala Mathematical Association. We are fortunate to exist in an era where our mentor, Professor A. Vittal Rao, shares his presence, lectures, and talks, enlightening us along the way. In the gracious presence of all of us, we honor a truly inspiring teacher whose inevitable style of teaching and extensive knowledge in mathematics has touched our lives in many ways. May I request our Father Director, our Principal, and General Secretary of Kerala Mathematical Association to come forward to honor Professor R. Vittal Rao. I request Professor R. Vittal Rao to accept our honoring.
Gurur Brahma Gurur Vishnu Gurur Devo Maheshwara Gurur Sakshat Parabrahma Tasmai Shri Guruve Namaha Tasmai तस्मै श्री गुरुवे नमः.
Varadacharya Kannan, V. Kannan for short, son of Varadacharya N. Kannan and V. Rajalakshmi Kannan, was born in 1946 in Tanjavur, Tamil Nadu. In 1965, he earned his mathematics degree from National College, Tiruchirappalli, ranking first in the college and second in the university. After his post-graduation in mathematics from National College, Tiruchirappalli, in 1967, he took an MPhil degree from Madurai University. He received his first rank for both the MSc and MPhil program at college and university, respectively. In 1971, he secured PhD degree from Madurai University. He started his career as a lecturer in mathematics at Madurai University in 1972 and became a reader there in 1976. He joined as reader of University of Hyderabad in 1978 and was promoted to a professor post in 1985. He served the University of Hyderabad in the capacities of Dean, Pro-Vice Chancellor, and Vice Chancellor in charge. Professor V. Kannan has published about 70 papers in reputed journals. His area of specialization in mathematical analysis, topology, and topological dynamics, etc. As a research kid, he produced around 15 PhDs and graded 8 MPhil dissertations and 12 summer projects. He received many honors and distinctions such as Fellow of Indian Academy of Sciences, Fellow of Indian National Science Academy, Fellow of National Academy of Sciences, UGC National Lecturer, UGC Career Award for Young Scientist, President of Indian Mathematical Society, President of Mathematical Section, Indian Science Congress, ISCA Platinum Jubilee Lecture, and like many awards in national and international levels. He has been a member of many academic bodies. A few of them are member of Scientific Advisory Committee for MHRD, Government of India, member of Sectional Committee for Math Sciences, Indian Academy of Science, member of SARC Science Olympiad Program Committee sponsored by UNESCO. Professor Kannan is a passionate and inspiring teacher. His systematic nature and research interest in mathematics made him popular all over the country and even abroad. He continues his academic activities with much enthusiasm even after his retirement. Currently, he is serving as Professor of Mathematics at SRM University, Andhra Pradesh. He has given many invited talks on various topics in mathematical analysis, topology, and topological dynamics at conferences and workshops at national and international level. His lectures and talks start from fundamentals and goes into depth as time goes on. His absolute dedication to the discipline of mathematics has paved the way for enriching the mathematical talents of many students. His simplicity, profound knowledge, and dedication is remarkable. He is a role model for the entire mathematical fraternity. He has visited Rajagiri School of Engineering and Technology many times. He has given lectures in many conferences organized by Kerala Mathematical Association. We have the good fortune to live in an era where our Guru Professor V. Kannan ignites our minds and inspires us with his presence, lectures, and talk. In the presence of all of us, we honor an incredibly inspiring teacher and whose love for mathematics is equal by his love for his students and whom we look up to the deep appreciation and respect. May I request our Director, Principal, and General Secretary of KMA to honor Professor Kannan, and I request Professor Kannan to accept our honor.
गुरुर्ब्रह्मा गुरुर्विष्णु गुरुर्देवो महेश्वरा गुरु
Kabil Dattatreya Joshi, KD Joshi for short, son of Dattatreya Mahodaya Joshi and Nirmala Dattatreya Joshi, was born in 1947. Is born in 1947 in Ratnagiri, Maharashtra. He is a distinguished mathematician whose career embodies a rich tapestry of academic accomplishments and contributions to the field. Graduating with a bachelor's degree in mathematics from the University of Bombay in 1967, he embarked on a journey of intellectual pursuits that led him to Indiana University, USA, where he completed his postgraduate education in 1972. His doctoral dissertation focused on the non-symmetric generalization of the Borsuk-Ulam theorem. A significant portion of Professor Joshi's career was dedicated to IIT Bombay, where he served as a faculty member for almost 4 decades from 1975 to 2013, and he was involved in the conduct of JEE for over 2 decades. Throughout his academic career, he made a significant contribution to the field of topology and number theory. He authored many research articles in topology and number theory. During his tenure, he not only imparted knowledge, but also received the prestigious Excellence in Teaching Award in 1997, underscoring his commitment to an effectiveness in educating the next generation of mathematicians. His impact extends beyond IIT Bombay, as he later assumed the role of Professor Emeritus at the College of Engineering, Pune from 2014 to 2016. Professor Joshi's influence is not confined to the realm of academia. He was left a lasting imprint through his written books. His authored books, including Introduction to General Topology, published in 1983, and the more recent one, Multivariate Calculus through Linear Algebra in 2022, showcase not only his mastery of mathematical concepts, but also his ability to articulate complex ideas in a comprehensible manner, contributing to the broader dissemination of mathematical knowledge. As far as mathematical community is concerned, of Kerala is concerned, his book, General Topology, is a prescribed book for the topology course in many universities and is well known among students for many years. Furthermore, Professor Joshi's versatility is evident in his contributions to both pure and applied mathematics. His adeptness in addressing a spectrum of mathematical domains underscores the depth and breadth of his expertise. His academic excellence, reflected in his early achievements as the topper in Sanskrit in SSC and BSc, further solidifies his reputation as a luminary in the mathematical community. Professor K.D. Joshi's career is characterized by a harmonious blend of academic achievement, teaching excellence, and impactful contributions to mathematical literature. His enduring legacy as a mathematician of eminence continues to inspire and shape the landscape of mathematical inquiry. The respect and love of students towards Professor Joshi was seen when he visited Rajagiri School of Engineering and Technology in 2019 to give a talk. We are fortunate to have the privilege of grasping the basic concepts of many areas of mathematics domain under the guidance of the inspirational mentor, Professor K.D. Joshi. In the gracious presence of all of us, we honor an exceptionally inspiring researcher whose absolute dedication to the discipline of mathematics has paved the way for enriching our knowledge and showing us the path to traverse. May I request our director, principal, general secretary of KMA to come forward to honor Professor K.D. Joshi, and may I request Professor K.D. Joshi to accept our honor.
गुरुर्ब्रह्मा गुरुर्विष्णु गुरुर्देवो महेश्वरा गुरुर्साक्षात् परब्रह्मा तस्मै श्री गुरुवे नमः। तस्मै श्रीगुरुवे नमः।
Achyuta Krishnamurthy, son of Mr. Achyuta Varrier and Miss Parvathakutti Amma, was born in 1948 in Kottayam, Kerala. He emerged from a modest background, being raised with discipline. After completing his graduation in physics, he developed a keen interest in mathematics and earned his master's degree in mathematics in 1971 from CMS College, Kottayam. His academic journey reached its pinnacle when he was awarded a PhD degree by Annamalai University, Tamil Nadu, in 1978 for his thesis entitled Branching Process with Immigration and Disasters, guided by Professor G. Shankaranarayanan. Driven by a desire to serve the nation, Professor A. Krishnamurthy began his career in the Department of Mathematics and Statistics at Cochin University in 1978 as lecturer in applied mathematics. He ascended through the ranks, becoming a professor in applied mathematics in January 1987. His research interests encompass stochastic modeling, analysis, and application with a focus on queues, inventory, reliability, mathematical finance, and branching process. Upon retiring from formal service from Cochin University of Science and Technology in April 2019, Professor Krishnamurthy continues his academic pursuits as honorary emeritus professor at the same institution. He later served as a visiting professor at Department of Mathematics, University of Calicut from 2012 to 2013. Notably, he was recognized as an emeritus scientist by Kerala State Council for Science, Technology and Environment, working from November 2013 to October 2016. Academic journey of Professor Krishnamurthy took an international turn when he became an emeritus fellow of the University Grants Commission in April 2017. He was the principal investigator of an Indo-Russian joint scientific project on telecommunication at CMS College, Kottayam. This collaboration reflects his gratitude to CMS College, his alma mater. Throughout his career, Professor Krishnamurthy achieved recognition for his scholarly contributions. He was chosen for the UGC Research Award while he was a professor at CUSAC. He organized 15 conferences during his tenure as a teacher, 3 of which were national and 12 of which were international. In February 2009, an international conference was held in honor of Professor S.R.S. Varadan of the Koran Institute of Mathematical Sciences at New York University, USA, in recognition of his selection for the esteemed Abel Prize in 2007. As a research collaborator, visiting professor, plenary speaker, invited speaker, and contributor to conference paper presentations, he traveled to 22 different nations and approximately 40 universities and institutions overseas. Currently, Professor A. Krishnamurthy serves as the honorary director of the Center for Research in Mathematics, CMS College, Kottayam, actively contributing to the academic and research endeavors in the field of mathematics. He has visited Rajagiri School of Indian Technology and given lectures in many conferences organized by Kerala Mathematical Association. We are privileged to benefit from the enlightenment brought by Professor A. Krishnamurthy through his insightful lectures and talks. With the permission of all your and permission and presence of all of you, we honor an immensely inspiring teacher whose distinct style of teaching and ardent passion for research are unparalleled and has left an incredible mark for all of us. May I request our director, principal, General Secretary of Kerala Mathematical Association to come forward and honor Professor A. Krishnamurthy. May I request Professor A. Krishnamurthy to accept the honor.
Gurur Brahma Gurur Vishnu Gurur Devo Maheshwara Guru
We wish all our gurus a prosperous and healthy life, and we wish they will contribute more to mathematics community. Now, I request Professor A.R. Rajan, formerly of University of Kerala, for the felicitation.
Honorable and respected professors, Professor V. Kannan, Professor Vital Rao, Professor K.D. Joshi, Professor A. Krishnamurthy, the Director of the Rajagiri Institute, Principal of the Rajagiri Institute, Professor Paul Isaac, General Secretary of the Kerala Mathematical Association, distinguished participants, my dear colleagues, friends, and delegates of the conference. So it's a very great honor, I consider, to be here on this felicitation of four great mathematicians of our time. As the citations have been read out here, so we come to know more about these professors, and of course, about some of them at least, I would say, I personally, and I'm sure the mathematics community of Kerala are much familiar. I would particularly mention Professor K.D. Joshi, the name being very familiar to most of us through the book on topology he has written. And I would say this may be, I think it is the second time I meet him, but as a real meeting, I think it is the first time, in the sense that when I visited IIT Bombay in connection with the retirement program of Professor Limaye, who again is known to the mathematics community here through his book on functional analysis. So that time, I just happened to see Professor Joshi, but I don't think I have talked to him. I was with Professor Nambudiri, Narayan Nambudiri. He has been a former student of Professor Joshi also. And Professor Kannan, I have known him for several years now, starting with seeing him at conferences while I was a very junior researcher. I have met him, I would say, I don't say there's a meeting, but I have seen him addressing the conferences, one in Kusat, then in Kerala also, and in many places. And later on, I could be more close with him to the extent that we were both speakers in several events, one in Hyderabad, last one, I would say, in a Andhra Pradesh Teachers one conference. I was there, and he was also a invited speaker there. And I had the opportunity of receiving his hospitality while he was a Pro-Vice Chancellor of the Central University. I visited there and I could stay in the guest house, and he was very kind to provide me facilities. And Professor Vital Rao, I would say, I know his name, not personally, I have been with him. And I'm happy that he is here to receive our honor. But he also is a very eminent researcher. I have known his research field. And I'm very happy that I could be here in the honoring function which is given to him. And Professor Krishnamurthy, actually this word sometimes is misspelled. That occurs in Malayalam, that's all. Okay, Professor Krishnamurthy. He has been, I would say, very closely known to me, being where he was in the Cochin University. I also was a very frequent visitor to the Cochin University, with, of course, the kind invitations of several people here, Dr. Vijaykumar, Dr. Romeo, Professor Nambudiri, all have invited me several occasions, including Professor Krishnamurthy. And he has been associated with some of my programs also. While I was in the Kerala University, he was a member of our advisory committee for the SAP, and in several ways. And I have been knowing him as a very active researcher, and he is still on that field. So I would place my respects on all these four professors and wish them better things in life in the coming days. I would also especially mention the efforts taken by the Rajagiri College Mathematics Department, headed by Professor Vinod Kumar, both in organizing this conference and in designing this type of a honoring function. As he has mentioned, one of the previous functions has been in 2013 in connection with the Conference of Indian Mathematical Society, where my guru, I would say, my supervising teacher, Professor K.S. Namburipat, was among the people who were honored at that time. At that time also, the senior people like Professor Thirukraman and Professor Sriramakrishnan were also honored in this college. So I would express my happiness over the organizing this type of programs in this institute, and I would congratulate the director, the principal, and all the faculty members and students. I have seen that I was here from yesterday. I see that all the people in the maths department, the faculty, students, all are very much involved in making the program, the conference here, a successful one. So congratulating all of them. I conclude. Thank you.
Thank you, sir. May I request Professor A. Vijaykumar for the felicitation.
Respected gurus on the dais and my dear students, I have a very long association with all the three members present here, and I knew Professor Joshi only from Rajagiri last 4 years. I have plenty of stories to tell, but I'm limiting to some personal anecdotes that connects all these great gurus. My association, or rather, Professor Krishnamurthy was my teacher in Cochin University in 1978. And I remember some classes of him in those days. And the mathematics that he taught, that is now I am using, is Markov chains. Professor Kannan and 4 others, my academic guru, Professor Abdi and Professor Thirukraman, and my PhD examiners, Professor Kannan and Professor Unni, were so generous that I got PhD degree. And they did one more thing, maybe because I may fail in the Viva. In the history of Cochin University, only 2 cases are there where the examiners told that there is no need for a Viva. Thank God, or thank them. Professor, how do you remember the teachers? By hearing their classes. And I told Professor Kannan yesterday that I still remember your talk on dispersed sets and also construction of Cantor set, which he taught as early as 1980 when he came to Cochin University. So I had these several occasions to interact with Professor Kannan, and even now I do that. So they are inspiring teachers. There are several people who teach mathematics and read mathematics, not as inspiring as two of my gurus, Professor Abdi, Professor Thiruvikraman, and of course Professor Kannan, Professor Vittal Rao. They all belong to that category. About Professor Vittal Rao, my association is about 35 years. You may not remember, but I still remember younger Professor Vittal Rao holding a yellow book on SL2R, special linear group of 2 by 2 real matrices. That was a graduate textbook's yellow color. He was holding it along with my another friend of IASC, Professor Poolan Prasad. I knew Professor Poolan Prasad earlier than Professor Vittal Rao. They used to move together always in IASC maths building. So Professor Poolan Prasad introduced me to Professor Vittal Rao, saying that he is so-and-so. And one information which I have from IISc is that he is one of the very few teachers in mathematics in the entire IISc whose classes were attended as number as 500 or 600 registered. Professor Unnikrishnan agrees with that. So he was a very inspiring teacher. He has come to Cochin University for several programs and many programs that are organized by the department and the conferences and so on. About Professor Joshi, I am not taught topology from his book. We had Thorpe's book. But there is it's always exciting to meet an author. There is a joke that one of my students shared. There was a program in my college, Chitru College, where Professor Kumaresan was also present. So in the feedback section, I asked that student who later on became my student, what is so exciting in this workshop? So he said that I am very excited to meet Professor Kumaresan. So we asked him, why is that so excitement? He and like many others felt that all authors of books are no more. So he was seeing physically one author live. So that is the excitement. And I definitely share this idea. Meeting an author is always a great excitement and pleasure. So, as I said, if we want to thank or wish many more years of academic activities for inspiring us to become role models of teachers, this next generation need these teachers for not teaching mathematics, but inspiring to become great mathematics teachers. So as I told in the beginning, whatever mathematics that I studied and I propagate, thanks to 4 people in particular, and all the teachers from Cochin University who taught me from 78 to 80 for my master's and later on for PhD. Some of them became my colleagues also. So that was a great honor that I had to work with these great teachers. And as I repeatedly remember, the generosity and kindness that Professor Kannan and Professor Unni had towards me made me stand before you and say a few words about them. So I wish many more years of long, vibrant academic activity to all these teachers. There is a saying that there is no retirement for teachers. They keep on teaching. And hope that they will come to Cochin more number of times and enlighten us with more ideas. Thank you.
Now, may I request Professor R. Vittal Rao to speak a few words. As Professor Krishnamurti said, I'll keep this on. It's a little cold here. Okay. First of all, I didn't expect that I would be asked to say a few words here. I would express my sincere thanks to the Rajagiri School of Engineering and Technology and the Kerala Mathematics Association for this honor, which I know for sure that I don't deserve. Anyway, I tried to avoid this by telling Professor Vinod Kumar that I may not be able to come, but it's very difficult to persuade Vinod Kumar. So finally, he succeeded in. It's difficult for me nowadays. For the last few months, little difficult to come out of Bangalore. So I said I'll come in the morning and the evening and return in the evening. I thought he would reject, but even that he accepted. So there was no escape from this. Anyway, I'm really thankful to you for putting me in the same class as my distinguished colleagues, Professor Kandan, Professor Joshi, and Professor Krishnamurti. I consider it's a great honor. And I have enjoyed every bit of my life as a teacher in mathematics. And I have learned a lot from my students, from my colleagues, and I have some very long association friends here like Professor Vijay Kumar, Dr. Unnikrishnan, Professor Narayanan Nambudri, and many others, Professor Krishnamurti, of course, and all the distinguished guests on the stage. I have enjoyed every bit of my time in life in teaching mathematics, and it's always a pleasure to see that your students go way ahead of you and you are left behind, and you start trying to catch up with them, learn from them every day. So you stop. My only thing that I have learned in my life is that you stop being a teacher the day you stop learning. Okay. So we are a constant group. We have to be a constant group of learners and teachers. And I wish to thank all of you. And I hope a great future for the Kerala Mathematics Association and all the maths teachers here. Thank you very much. May I request Professor V. Kannan to address the audience.
First, let me thank both the Rajagiri Institute and the Kerala Mathematics Association for giving me this opportunity to be honored. In fact, I am really honored. I feel honored. I have been observing that unlike other mathematical associations of other states, Kerala Mathematical Association has always been very active since many years. And I have also been a part of its activities several times. Professor Trivikraman, who was behind the activities of almost all activities of Kerala Mathematical Association, was my good friend. We were co-research scholars in Madurai University, and that may be a reason that brought me to Kerala more often. Almost every year I used to come for some activity or the other, and for Kerala Mathematical Association's annual meeting itself, I have come several times. Therefore, I am congratulating the Kerala Mathematical Association and wishing that it should continue its activities further and further. Actually, today, this association and this institute has honored 4 persons from 4 different states. That itself speaks how Kerala Mathematical Association is active. It doesn't confine itself to Kerala. At the end, I am once again thanking the Rajagiri Institute and also the Kerala Mathematical Association for this opportunity. Thank you.
Thank you, sir. May I request Professor K.D. Joshi to speak a few words?
Okay, all mathematics lovers. It is customary, I suppose, while addressing speech of acceptance, to say that I am really not qualified for this honor, but I feel rewarded. Well, that first part that is very true. I'm really not qualified. And at the same time, I feel rewarded. So that might sound contradictory, but no, there is a reason why I feel really rewarded today, because consistently I adopted a certain doctrine in my career. And this is probably the first time that I see some acknowledgement of it at this type of gathering. Well, the doctrine is to break the myth which was prevalent and which is now prevalent about the role of teaching and research. The common theme is, the common cliche, I should say, is teaching and research go hand in hand. Well, that is true. But in what sense? What is done by researchers today, a lot of it will be forgotten by tomorrow. At least in mathematics, that is the case. But the part which survives, the part which deserves to survive, it is for the teachers to reach that part to the common students. That is the purpose of the teachers and the purpose of researchers. That is how they two go hand in hand. It is not that you can't be a good teacher unless you are a good researcher. That is wrong. I used to tell in every interview I appeared and where I was denied the promotion that I don't agree. Why should we? It is like saying that you can't be a good batsman unless you are a good bowler. But then why do we have people like Tendulkar? Of course, we do also have people like Kapil Dev who are good in both. But that doesn't mean that they have to be together. These are separate qualities and each has its value. So you judge it on the basis of that quality rather than saying whether you are also good at this or that. No. So this is the principle I consistently followed, and naturally it was not acceptable, especially to the examiners or persons sitting on the other side when I appeared for any interview, but I stuck to that. So one thing I have not done is doing any great research. I have not done that. I don't claim to be, and I don't think anybody can say that about me. As was said, I'm better known by my books, and I feel rewarded. If a person is known by books, that is not bad. At one time, in an interview, I said there were some very reputed persons who were conducting the interview. I said, my way of looking at things is like this. If you are a Ramanujan, well, that's great. Don't do research and nothing else. Don't even think of anything else. But if you are not a Ramanujan, don't try to pretend that you are Ramanujan. Instead, if you can be a Karmarkar, well, that's good enough. Karmarkar, as some of you might know, he invented the polynomial time algorithm for linear programming. But if you can't do anything great research, anything really useful, then be a Shantinarayan. That was my idol. Now, Shantinarayan books may not be familiar to the younger class, but he was a stock name. On most of the standard results, standard papers, he would have a book. So I realized that that is where I really can do something and contribute, rather than just churning out papers after papers and proving half a dozen fixed point theorems every year. No, I decided not to do that. So it is really an honor to feel that despite this, I'm getting this reward. So thank you so much. Thank you, the Kerala Mathematical Association. I really feel rewarded.
Thank you, sir. Professor A. Krishnamurthy.
Thank you very much for honoring me, especially on the occasion when three great stalwarts are honored. I'm really a dwarf. But anyway, it so happened that I turned 75 last December, and therefore Professor Vinod Kumar was kind enough to include me also in that list. On this occasion, I have one request. Kindly provide some blanket. I feel so cold inside. Professor Vittal Rao and myself got quite comfortable after getting this shot. But, my friend, Professor Alexander Dudin, is head of the mathematics and computational department at a State University of Belarus State University, Minsk. So whenever we get into some AC rooms, I would say we are entering Siberia. He would immediately say, I like Siberia. Anyway, I do not know whether I have inspired my students, especially the master's students. I had a brief stint of about 9 months at Farouk College, Calicut, where I turned out to be a good teacher. Thereafter, I cannot recollect any occasion when I turned out to be of that type of teacher. During my teaching career, starting at Kochi University in October 78, going up to April 2009. About my research potential, of course, my research students should comment on, not myself. But I'm fortunate to have so many students who interacted with me, and I learned quite a bit from them. And that resulted in writing a number of joint papers or even single author paper. Probably with that, I gained quite a bit. And my students also might have gained something out of that. I'm still trying to do something. I don't know whether still I'm inspiring my research students, but I try to do some work jointly with them and independently as well. As long as I can, I would like to continue in this and continue to be associated with the Kerala Mathematical Association as well. Thank you very much for honoring me, especially the Rajagiri institution and also the organizers of this program. Thank you.
Thank you, sir. Before concluding the session, may I request Professor Vittal Rao, Professor Kannan, Professor Joshi, and Professor Krishnamurthy to pose for a photo. Thank you, and we conclude this session. Next, we have the proceedings of the general body meeting and other activities of Kerala Mathematical Association.